Welcome to Chapter 3, IPv6 Addressing, Representation, and Addressing Type. These PowerPoints were prepared by Rick Graziani, so I do want to thank him for both his textbook and these PowerPoints. Again, this is off of the IPv6 Fundamentals, a straightforward approach to understanding IPv6, written by Rick Graziani. Again, thank you. You can find additional of his support material both with the videos and the chapter book as well. So the first part of this, we have to understand hexadecimal numbering systems. That's a huge part of understanding IPv6. So let's go ahead and get into the numbering system rules. So all of the number system's first 4 digits begin with a 0. A base n numbering system has n number of digits. Decimal begins, or as a base 10, digits are 0 through 9. So there's 10 actual digits there. Binary, same thing, 0 and 1. Hexadecimal is base 16. The first column is always the number of ones. Each of the following columns is n number of the previous columns. So n equals base n. So here we have base 10. That's 1, 10, 100, 1000. Here we have 1, 2, 4. Because again, you'll notice they increase here by 10, that's base 10. Here they're doubling because it's times 2. Base 16, same thing. 1 times it by 16, 16 times 16, 256, 256 times 16, and so forth and so forth. So with base 10, if we want to represent a number with a single digit, we can only do the first 10 numbers. With hexadecimal, if we want to signify each specific number with a single character, we can do up to 16 numbers, 0 through 15. Because again, hexadecimal starts with 0, 16 digits, it'll be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then when we get to 10, because again, we want single digits, 10 will represent A, B will 11, C will be 12, D will be 13, E will be 14, F will be 15. Again, because we started with 0, we have 16 digits. The nice thing is, in hexadecimal and in decimal, we can always convert them back to binary. And again, in binary, it's going to be 4 bits, because 4 bits will range between 0 and 15. So, the first number 0, 1, 2, 3, all the way to F can be represented in binary, again, using the first 4 bits. So let's move on to representing an IP address. First of all, an IP address is how many groups of 4 hexadecimal numbers. So we have 1 group, 2 groups, 3 groups, 4 groups, 5 groups, 6 groups, 7. We have 8 groups. Each one of these is a hexadecimal number and 4 bits. So we have 4 digits. Each one is 4 bits. So each group of 8 is actually a 16-bit number. So we're always going to break down individual numbers. Back to that 4 binary bits. So a lot of the times people have been calling these hextets, and they're not official yet, but that's a common term. And they can range between straight zeros and straight Fs. And again, we have 8 groups of them. Each group is separated by a colon. Reading and subnetting IPv6 is a lot easier than IPv4. That's kind of subjective, but we have to start talking about some rules with IPv6 so we understand kind of how we can represent these addresses. So again, as we start looking at them, it's 128 bits total. So let's look at a IPv6 header. Again, the headers here are more simplified. We have the first 64 bits We have source and destination addresses, and that's really it as it relates to our headers. Again, heading information in an IPv6 packet is way simpler than IPv4. So let's look at the number of addresses. So with IPv4, we had roughly 4 billion. With IPv6, we have 340 undecillion. In reality, that's 340 undecillion, 282 decillion, 366 nonillion, 920 octillion, 938 septillion, 463 sep, then sex, then quint, then quad, then trill, then bill, then million. So, I mean, 340 undecillion addresses, that's a lot. Another way is 340 trillion addresses. 10 non-million addresses for every person on Earth. Or, you get the point here. There are a lot of addresses. So let's look at some rules for helping manage IPv6 better. So 2 rules for reducing the size of written IPv6 addresses. First of all is the leading zero rule. In any 16-bit segment, you don't have to write leading zeros. So we can remove all of those. So you'll notice in the third group of leading zeros, we remove the first 3 leading zeros. But to help keep this organized, we actually leave the 4th 0 in place just to make sure. Any leading zeros we can remove. What happens when we have a huge string of zeros that we want to get rid of? That goes to the next rule. Owning leading zeros can be excluding, trailing zeros can't be, because it makes this more ambiguous. For example, if we are able to do leading and trailing zeros, is it 00AB? Is it AB00? Is it 0AB0? We don't know. That's why only leading zeros can be removed. Because again, these can all represent special things. So now let's move on to the second rule. We can reduce the addresses even further by any single continuous string of one or more of 16-bit segments of all zeros can be removed and replaced with a double colon. So here we have a string of 4 groups of zeros. We can get rid of them and the leading zeros, so we can rewrite the address 2001 db8 1000 : 1. Remember, the big thing here is we can only use the double colons once. While the RFC 5952 doesn't state the longest string of zeros has to be replaced, a common practice is the first set. So here we have 2 sets of zeros. We can only use the double colon once. So we're going to use the first 2. And we're going to remove the leading zeros. Or we go to the second 2, and then we'll remove the leading zeros. Both are correct. The maximum reduction of the address is known as the compressed format. So do keep that in mind. This is known as the compressed format. So using the double colons more than once can create some ambiguity. So different combinations depending on where the double colons are. That is why you can only use double colon once. So let's go ahead and look at the prefix length. So with an IPv4 address, the prefix length for the network was typically 32 bits. That's the portion of the address that can be identified by a dotted decimal subnet mask, the prefix length, and that allows us to know the number of bits in the prefix or network portion of the address. So /8 let us know that we're using the first 8 bits for the network and the remaining 24 bits for the hosts, so forth and so forth. Here at /24, we're using the first 24 bits for the network, and we're using the last 8 bits for the hosts. So an IPv6 prefix always identifies the prefix length, and it's normally done in dotted decimal form. Alright, so the prefix length is the number of bits in the prefix portion. Again, that's going to be the equivalent to the network portion of the address. That separates the prefix portion from the interface ID, which is the equivalent to the host portion. So here again, we have essentially host and network, but we call them prefix and interface. Let's assume we have a prefix of 32 bits. So first of all, we're going to write out the immediate address with no spacing. The prefix length will be 32 bits. Each group of 4 hexadecimal numbers is 16 bits, so we're going to use the first hextets, meaning the remaining portion is there for the interface or the hosts. If we do a 42-bit one, it'll be there. If we do 52, 56, because again, each number is 4 bits. The prefix length does not have to fall on a nibble, so it doesn't have to fall on a 4-bit boundary. So it doesn't have to fall on a nibble boundary. So here we have an example of a /60, /64. But what happens if we went to /62? Well, it would be between. But because of the large address space, we don't have to worry about going to a /64. We can stay on those nibble boundaries without an issue. Because again, 62 would fall in there. Would have to use the first 2 bits. Totally possible for a prefix and interface. But again, not the best way. So let's look at some prefix examples. Here are some device address examples. Notice up here we have double colons and no number at the end. That's because the numbers at the end would be our host bits. So, first of all, we're going to get more familiar with these addresses, or these types of addresses, because they are global addresses. We're going to learn more about that in the next lesson. So now let's get over to an overview of IPv6 in general. So RFC 6724 is the default address selection for IPv6, and that includes IPv4. We're going to talk about that on other lessons, but big thing here is IPv6 does not have a broadcast address. However, there is an all IPv6 device multicast address, which we'll explain that in lesson 6. Like IPv4, we have a unicast, we have a multicast, but here instead of a broadcast, we have an anycast. So unicast, we have a global unicast, we have a link local unicast, we have a specific loopback, we have an unspecified, we have a unique local, and we have an embedded IP version 4. So some of these are important, like global unicast, those are globally routable addresses, where link local is not. But each of these actually shows you their prefix and the appropriate beginning networks that they should fall on. We have some multicast addresses, which are unassigned, and a solicited node. Again, pay attention to the appropriate addresses. These are very unique and do not change. And we have an Anycast, because again, IPv6 doesn't do a broadcast. So we're talking about, one too many. We're talking Global Unicast next lesson, Link Local lesson 5, Multicast lesson 6. So there are more details on this. So again, IPv6 sources, always a unicast address. And here are, again, the packet headers. Okay, here we have source destinations, but again, you have to remember that source addressing for IPv4 and 6 are different because of the address space. IP version 6 destination could be a unicast, multicast, or anycast. IPv4 could again be multicast, unicast, or broadcast for IPv4. Alright, so global unicast, again, lesson 4. We're going to talk about the different addresses for global unicast. We're going to look at very specific ranges of addresses. These are the addresses that we're going to be referring to the most, which will be 2000::3 and 21 dB8. Link local, more in lesson 5. This is going to be the FE80:10. This is not routable off the link. The link is going to be a local or private network. It's unique only on the link. An IPv version 6 device must have at least a link local address. It's used by hosts to communicate to other networks. Its router's link local address is used by the host as a default gateway. So even if it has a global address, it's going to be using its link local address. Adjacent routers will exchange routing updates. And next hop address in the IPv6 routing table. Alright, moving on is our loopback. Again, that's a ::1. It's similar to a loopback in IPv4. It's in the IPv6 packet to itself. Same functionality as the 127.0.0.1 loopback address. It's not routable. The unspecified address, all zeros. It indicates the absence of an address. It's used as a source IPv version 6 address during duplicate address detection process. The primary use of the unspecified address is for neighbor discovery process. It's specifically during the duplication address detection process, can also be used as a source address in a router solicitation message, or a router advertisement message should always be or have a legitimate address for a source address, not a unspecified. Alright, let's go ahead and move on to our unique local addresses. So there is going to be an FC00:7. It's similar to the 1918 RFC for IPv4, but it's not meant to be translated to a global unicast. It should not be routable. It's to be used in a more limited area, such within a site or device inaccessible from the global internet. We can use the remaining bits for our hosts. It is assignment type 1. It's normally a self-selection of a 48 prefix. It is not coordinating. It's not a global quad A or pointer DNS record. Its essentially assigned address is, again, FC00 prefix of 8. Note this is a site local address, is an FEC0:10. Have to love some of these because this is not really well defined and not normally used heavily. Embedded version 4 for IP. It's going to have all zeros for the 96 bits, and then the IPv4 address will be the remaining 32 bits. Was used to dual stack devices to support both IP version 6 and 4. It's rarely used and is now depreciated. Other methods are used. Alright, so let's look at multicast. Let's go ahead and move on to multicast. Multicast is used to send a single packet to multiple destinations. It's more of a one-to-many. It's assigned a multicast address, again, more in Chapter 6, of an FF02:8. This is a multicast address with a link local scope. It's similarly assigned to a multicast address in IPv4. Here we're looking for an FF02:1, that's for all IPv6 devices. FF022, all IP6 routers. FF025 is all OSP version 3 routers, and so forth. Next, let's talk about a solicited node. Solicited nodes are a multicast address, again, more in Lesson 6. That's an FF02:000001 FF00. This one's going to use a prefix of 104. It automatically creates using a specialized mapping of the device's unicast addresses. It also has every global unicast and link local unicast has the associated solicited node's multicast address. And it's used during the ICMP version 6 neighbor discovery, using very similar to ARP and IPv version 4. We're going to talk a lot more about this in lesson 6. Let's talk about Anycast addresses. Anycast addresses, it's a unicast address that's assigned to more than one interface, typically at different devices. Here we have a best path selected by a router. If we have 3 resources all with the same address, it's similar to an IPv4 Anycast packet. It's a packet that's sent to an Anycast address is routed to the nearest interface, having that address according to the router's routing table. So in summary, unicast, multicast, anycast, again, global unicast, link local, loopback, unspecified, unique local, embedded. We talked about assigned and solicited. We also talked about anycast. We also laid out where all of them are going to be. Again, these are the PowerPoints for the IP version 6 fundamentals, a straightforward approach to understanding IPv version 6. And again, I want to thank Rick Graziani for providing with the PowerPoints and for writing the textbook. Thank you.